Ok, ben bonjour à tous. Good morning, everyone. So, je vais faire la présentation en anglais, mais s'il y a des choses qui posent problème, n'hésitez pas à demander. Le problème, c'est surtout moi qui n'ai pas l'habitude du tout de faire des présentations en français, donc je pense que la présentation sera sans doute beaucoup mieux en anglais. Okay, so good morning, everyone. So my name is Guillaume Jacquement. So I'm a group leader at Åbo Academy, which is a small university in Finland. And I will be presenting the zero-cost deep learning for microscopy platform. And actually, we're going to spend quite a bit of time together today. So hopefully you get a good idea on what the platform is about and the kind of thing you can do with it. So unfortunately, I couldn't come to La Rochelle today. I'm sure you guys have a really nice weather and hopefully you have a nice time there. But since I just wanted to show you a little bit from where I'm calling you from. So I'm here in Turku in Finland, which is right at the end of Finland. It's one of the most southern parts in Finland. And here is just some pictures that I took just to show you what the city looks like. So it's really nice and sunny in the summer, and then it gets quite cold, and we have a bit of snow in the winter. And I hope that some of you, and maybe many of you, will be able to come to Turku next year because we are organizing the next ELMI meeting in June. So then if you're interested in ELMI, as hopefully many of you may be, then don't hesitate to save the date. So that will be in June. So you can come and see us in Turku. And we have some really nice activities as well in the archipelago here in Turku planned for the meetings. So it might be a nice trip for you guys to join now that traveling is starting to be possible. Okay. So I also wanted to share a little bit about the kind of work that we do in my lab. So I will be, of course, talking a lot about deep learning today, but that's only a really small part of what we do. So in my lab, we are mainly interested in cancer cell migration. And for that, we use a lot of microscopy strategies to look at that. So here is just an example of an ovarian carcinoma cells migrating in 3D. And then we're interested in understanding how actin in particular is involved in directing cell migration. So just to give you a little bit of context and also to kind of explain why you see some of the images that I will show you later on. But that's not what I want to talk about today. So today here to talk about deep learning and microscopy. Why, so here is the kind of the programs that I put together for those 3 zero-cost deep learning for microscopy session. So with the first one being now, where I will kind of briefly introduce the zero-cost deep learning for microscopy platform, and then talk a little bit about TrackMate as well, and how we've been combining both to do tracking. And that's kind of basically the plan for the first session this morning. I will then briefly give you a tour and a demo of the platform. We'll showing you the StarDist notebook. And then after that, then I'll let you play a little bit with the new version of TrackMate if you've not done that already, on how to use StarDist in TrackMate to track cells. And then after your break, then we'll talk a little bit about something different that maybe you haven't talked too much about yet in this workshop, which is denoising, and a little bit about image-to-image translation. So for instance, using Pix2Pix or FNet. And then after that, then if you're interested in training your own denoising deep learning networks, then you have the opportunity to do that. So I've put some data sets for you to play with in the shared Google Drive for the workshop. And then this afternoon, then we can talk a little bit more about now quality control and metrics that are useful to consider when using deep learning. And then there we have a notebook to calculate those metrics. So then you can also have a look at that. And then I've put some example of that in the Google Drive folder of the workshop. Okay, so but if we get started now with a brief introduction on the zero-cost deep learning for microscopy platform. And some things that I'm sure you are all very well aware of, and that's the main reason why you guys are here in this workshop, is that deep learning has really exploded in the recent years to analyze images, and in particular microscopy data. So for us, the journey started maybe 2-3 years ago when we tried to kind of implement some of those super cool techniques that have been developed by others. Again, something that hopefully you are also really well aware of, but I think it's good to kind of touch base on, is how deep learning actually works compared to using, let's say, a classical algorithm when you want to analyze microscopy images. And here is an example of denoising as an application. So if you use deep learning to denoise microscopy images, then what you will do is basically you will take an image and then you will apply a crafted mathematical equations, a formula that will basically denoise your image. So then basically based on what you know from your image, and then you will try to improve it. So one of the simplest way to do it would be, for instance, to use a Gaussian deblurring strategy. Denoising strategies that will blur a little bit your image, but then still improve the quality of your images. So then here it's kind of in a simplified way, then you have an image and then you apply a mathematical formula to try to improve it. And that's kind of how most classical algorithm will work. With deep learning, the process is quite a bit different in the sense that first you need to train a deep learning model using a training data set. And then the deep learning model will learn how to do a specific task from this training data set. So here as an example, if you want to do denoising using this kind of strategy, what you very often needs to do is to provide images that are noisy, images of high quality, and then provide that to a deep learning algorithm. And then the deep learning algorithm will start to learn on how to denoise your images and to produce what's so-called a deep learning model. Okay, and basically inside of these deep learning models, you have thousands to millions of different adjustable parameters that control different image translations or modifications that will then change your image from A to B, so from your noisy to your high quality images. Then once you've trained this model, then you can apply it. So then you have a different type of noisy images, and then you can denoise them straight away. So then you can directly see there you have advantages and disadvantages. One of the disadvantages is that, of course, you need to train deep learning model. So then you have an extra step. But one of the main advantages is that, of course, you're now training an algorithm to do exactly what you want. And typically, those algorithms are actually really good at doing what you want because they learn what is the best way to do it, which is not always the case with those classical algorithms. But again, then you still have this problem here, which is training the deep learning model for doing what you want. And that can be surprisingly hard. So it's getting easier and easier because people are now developing tools to help with that. But here are kind of very often still the main things that you need to do in order to train a deep learning model. So you need to install the software and the dependencies. And that can be surprisingly hard because as you may have already seen through this workshop, that depending on the algorithm you want to use, there are very strict requirements in terms of the dependencies that need to be installed. And very often they are not compatible with each other. So if you want to install, let's say, CSV Deep Care, you will need a very specific version of CUDA and a very specific version of TensorFlow to run. But then now, if you want to install a different algorithm, let's say embed-seg, then now you need PyTorch, a specific version of Torch, and a completely different environment. If you do not have the background to get those things sorted, then it can actually be really difficult. So especially if you're a biology class like myself, you might spend quite a lot of time troubleshooting why your environment is not working. And then after that, you rarely have solutions that work straight out of the box. So very often you have codes that needs to be tuned and edited in Python in order to get your algorithm to work. And then you also need access to fairly powerful workstation if you don't want to train for weeks and weeks on end. then you need to have access to quite expensive equipment. And of course, if you work in the core facilities, then you might already have access to those workstations, but then again, it's not the case for the vast majority of scientists. So all of that kind of create a big barrier for people to start using those algorithms to analyze images. And honestly, when I started, this is how I kind of felt when I tried to first install CSB Deep Care in order to get it to work on my laptop. Then after a couple of days, we kind of gave up because we couldn't get them to work, and then we didn't have anyone to help us set up the environment. But then we team up with Ricardo Enriquez's team that we actually met through Twitter, where we kind of started to discuss that maybe there will be an easier way to get started with using deep learning. So that's kind of how we started working on the zero-cost deep learning for microscopy project, and then which is with those people that kind of started the project, and then after that, many others joined us or contributed one way or another to the project. But I won't kind of spend too much time describing what you can do with it, but basically it's relatively coming from a relatively simple idea, is that you just need a computer. It doesn't really matter what kind of computer you're using. You can do it on your phone as well if you're interested. And then you, of course, need data that you want to analyze. And then we basically use resources that are provided by Google. So Google uses those resources to promote their machine learning and deep learning libraries, but because they make those resources freely available, then we can take advantage of that. And then what deep learning, what zero-cost deep learning for microscopy really is a collection of notebooks, of Jupyter notebooks that run on what is called Google Colaboratory, which is an online platform that provides computing power to train machine learning and deep learning networks. And then you can, using those notebooks, you can train models, and then you can use them to make predictions. And then you can then download the data and use them with whatever software you like. So some of the trained model can also be used, for instance, in other software like Fiji, for instance, if you want to actually do the prediction offline. So it's a very simple concept in the sense that we are using resources that are provided for free by others. What you get is basically free cloud access to GPU provided by Google within limitation. You have a simple user interface that I will show you, so there's no requirement for coding if you do want to. And then if you, once you get kind of more comfortable with using those tools, then you can start modifying them if you want. And then there's basically a single platform for training, prediction, and quality control of deep learning model. And then I will show you a little bit more of that later. So of course, it's come with a catch, is that of course it's not unlimited free cloud-based access to GPU. So Google Colab, especially with the free version, you have a fairly strong limitation on for how long you can use it or how much data can be used. So it's not a solve everything solution, but it's a solution that can be useful to get started, or to try a new tool to see whether it would be suitable to analyze a specific type of data without having to install everything. Okay, so this is kind of what it looks like, and I will show you the web page again afterwards if you have not seen them yet. But at the moment, we have over 30 different Jupyter notebooks that cover a wide range of deep learning algorithms that can do a lot of different things, from segmentation, denoising, artificial labeling. You can also do some super resolution microscopy via, for instance, single molecule localization microscopy analysis, denoising and segmentation together, and so on, and then object detection with YOLO detection and RetinaNet. We also have one for image registration if you're interested in that kind of thing. Here is kind of, I had a video to show some of the things you can do with it, but then it doesn't look like it's here anymore. Let's see if it's because it's somehow hidden. Oh no, it's afterwards. But then what can you use it for? Then actually, you probably realize already, but that you can almost do any kind of image analysis task using deep learning. So anything you can think of that you do using, let's say, conventional algorithm, there's been now a deep learning network that's been created to do it. From object detection to image registration, image improvement, restoration, denosing, and segmentation. So typically deep learning is especially famous or used for segmentation because it's where it's really useful in a sense, because a lot of segmentation can be really challenging using classical approaches, but there's a lot of other things that can be also used, or other tools that can be used to do, or other tasks that can be used using deep learning. So here is kind of a short video that we put together last year, just to highlight some of the things that you can do using zero-cost deep learning for microscopy. And then you have example across the different image analysis tasks. So segmentation of different type of images using UNets, StarDist that you might have already had a talk from Martin about. So I will show you a little bit more example about that, on using StarDist to do segmentation and tracking. YOLO for instance, for object detection. So there it's more using bounding boxes. We will discuss a bit more about denosing and image restoration after the break. So here is, for instance, an example of noise to voids. Here's an example of CSB Deep Care, which was actually one of the tools that I really wanted to use in my lab when we got started with deep learning for microscopy. Here is an example of how to use DeepStorm for super resolution microscopy. So DeepStorm is one of those algorithms to do that. And then some of the maybe things that are a little bit less used at the moment, which is to use deep learning to do pseudo labeling or artificial labeling. So how to predict fluorescent labels, for instance, using other images. And here is an example of CycleGAN to do a little bit of super resolution microscopy. So just to kind of give you a brief overview of some of the things that are possible. Is there anything that you guys want to ask before I want to go to the segmentation and tracking part? So the aim there was really to kind of give a brief overview so that we can just slowly get started with the session.
Yeah, hi. I'd like to have two questions.
Sure.
You can hear me?
Yeah, I can hear you fine.
Okay. So do you? Oh, there's the camera. Hi. Is there any knowledge out there how long Google will keep the Colab free?
No, so there's absolutely no knowledge about that. But my educated guess, in a way, will be that I don't think they will stop it, because now they're starting to use more and more those tier system where you can pay to have access to more resources through Google Colab. So you had Google Colab Pro that was released maybe a year ago in the US. Now it's available in Europe as well, in many countries in Europe, including France, where you pay 10 euros per month and then you have access to more resources. But now they've just also released, I don't actually remember what his name, but it's like Pro Plus or something like that, where you have even more resources for more money. So my guess is that they will always keep the free version, and with the downside that they might put more and more limitation on the free version to force people to go to the paid version. So I don't think they will stop the free version at all, because they want to get people hooked on it. And then they will slowly push them towards the 10 euros per month subscription to use it more and more.
Legit, yeah, good idea. Then in the context of Deep Image J, we heard about yesterday, can we download the models which were created on the Google Colab?
Yes, so that's a kind of aim that we are kind of driving towards, and there are already notebooks where this is the case. So the Deep ImageJ team, in particular ST, has been working with us in kind of implementing exports for our notebook that works for Deep ImageJ. So then at the moment, there's already 4 different notebooks where the models that are trained using Google Colab here can be directly used in Deep ImageJ.
Thank you.
So the aim with also with the bioimaging with the bioimaging initiative is that if we can get funding for that, is that in the future a lot of those tools will be able to kind of talk to each other. So then if you kind of train a model in some of those notebooks, then you will be able to use them in Deep ImageJ, but also in Elastic and some of the other Fiji plugins. So that's the aim.
Okay.
Anything else you guys are wondering?
No.
No. Okay. Then I can carry on. So I guess so far in the workshop you've had a lot of I guess talks and also a discussion about segmentation, and in particular how to label images for training segmentation network. So I thought I'll just start with that. And just to highlight that we have quite a few deep learning notebooks that are dedicated for segmentation. So we have things like UNet, Stardist, and denoise-seg, so that does denoising and segmentation together, which actually improves segmentation quite a lot. So that's something definitely worth testing. And we also have a notebook for CellPose. And then if you're interested in interacting segmentation, where you basically have a deep learning model, in this case here, CellPose, that runs in the background and you can correct it so that you can further train CellPose. There's also a notebook here that was made by Romain Lane and Wei Wang together. So that works with Kaibu under the hood. So there's a nice graphical interface for that. As I said, I'm sure you've already heard quite a lot about segmentation. So the kind of things that I wanted to add a little bit here is tracking, which is of course something that's always useful to do for many biological applications, is to follow how objects change over time. And so we've teamed up with Jean-Yves Tinevez in Pasteur in Paris, that I'm sure many of you know. And then you and I in my lab together, we've been working on bringing some of those deep learning tools to TrackMate. So here I have to say that Jean-Yves is the one that did all the hard coding work on the TrackMate side. And then we were there to help him out with some of the application and also some of the deep learning side in Python. Earlier this year, we've released a new version of TrackMate that can now incorporate a lot of different tools that work with machine learning or deep learning that you've already heard about in this workshop. So, for instance, Elastic, Veka, Stardist, and CellPose, for instance. So you can now directly use some of either the result from those tools or the models trained in those tools directly into TrackMate for tracking purposes. So then if you start using some of these tools in your own project and you need tracking, then check the new version of TrackMate out. And so here is just some example of our own work on how we've been combining, for instance, here Stardist and TrackMate to do automated cell tracking for looking at cancer cell migration. So here is an example where we have cancer cells that are where the nuclei is labeled, which is perfect to detect using Stardist without too much effort. And then we can plug that directly into TrackMate to analyze hundreds of thousands of cells relatively without efforts to start looking at different migration parameters. Here is another example where we now use Stardist to track bright field images. So here, in this case, we have T cells, and one of the, I guess, useful things about T cells is that they're quite round, so they're still perfect to be tracked with Stardist, even in tracking the whole cells, not just their nuclei. And then we train using the zero-cost platform, start this model to detect and track those images, and then we've put that into TrackMate to do the tracking. So then again, that allowed us to relatively easily analyze quite a lot of data very quickly instead of doing manual tracking, which is of course always painful. Just here some example on how the data look like. So here is some example of our annotation to train the model, and then here the tracking with TrackMate. And then we could look at difference of migration on different conditions. So here the cells were plated on different in different conditions, and we could look at difference in their speed and motility in this context. And then something else that I think it's quite exciting in a way is that now there are some deep learning tools that can do segmentation on many different type of images quite out of the box. So when those work, then it's great to be able to use them. So here's an example on how we use cell pose to directly segment here our breast cancer cells, and then we could put the cell pose output in TrackMate to do the tracking. And then there, this new version of TrackMate is, of course, it doesn't work just with cell pose. It can work with any kind of labeled images. So if you start working with other segmentation tools like SplaineDist or EmbedSeg or any of the ones that you like, then you can import the label image in TrackMate to do the tracking. And the nice thing here is that you also get information about the cell shape over time, which can, of course, be useful for downstream analysis. So here I also want to say that if anyone wants to contribute to the zero-cost deep learning for microscopy platforms, then we are more than happy to hear from you. If you or your students want to generate notebooks for specific applications, then just be in touch. So actually one of the things we found is that generating and creating a notebook is actually a really nice project for master students or for interns. So if you have people like that may be interested in generating a notebook for specific applications, then let us know. Okay, on that, I just thank my lab. So they provided quite a lot of the data that I've shown you, and people that are funding our work here in Finland. But on that, that's kind of the short presentation I wanted to show you this morning before I give you a quick tour of the zero-cost platform, and before I kind of let you play with the TrackMates, the new version of TrackMate. Any question about the second part?
Yes, Guillaume, I've got one.
Go for it.
So you've been showing tracking, and I was wondering because on the video you had a specific label for static cells. Are you doing the classification and tracking using deep learning, or is the classification between moving and not moving done afterwards, after the deep learning has been done?
Yeah, so the classification is afterwards. So it's color-based in function of the speed of the track that you can do in tracking. So here the deep learning is only the segmentation part, I should say.
Okay.
The tracking itself is not yet done with deep learning.
Yeah, because we've been talking a lot about pre-processing and post-processing, especially when dealing with the deep image. So this is why I'm asking.
Yeah. Yeah, so then let's say the color coding of the cells in function of their speed is done afterwards in TrackMate, where you can classify like that directly on the image as well.
Okay, thank you. Additional questions?
Yes, I have a question. Could we make an offline installation of the notebook you made in zero-cost deep learning for microscopy? So
the short answer is yes, but you will need to modify it. So those are Jupyter notebooks, so they can run, of course, fine on another Jupyter environment, but there are a few things that are specific to Google Colab that will not work locally. So then there's some editing that needs to be done in the notebook itself.
And I think it's quite difficult for a neophyte of Jupyter Notebook or Python.
So if you've never worked with Python at all, then some of the notebook might be a little bit difficult. But at the same time, it's not something that you need to be, absolutely fluent in Python to be able to do it. Very often, some of the things that are specific for Google Colab are relatively easy to find and to modify. That say, if you want to do it locally, then the biggest issue that people have found is setting up the environment. So that always come back down to that, is that there's a lot of dependencies that needs to be installed properly, and if it's not done properly, then that causes a lot of issues in the notebooks. I think that's the hardest part, rather than modifying the notebook itself.
Okay, thank you.
So one thing that I should add on that is that we've slowly been working with people at EMBL that are also interested in setting up the notebook via binder to make it easier to set up on other type of, let's say, servers. But once it's in binders, then it's also easier to deploy locally. So hopefully in the coming months, we may have alternatives for people that want to set it up locally.
That's a very good news.
Okay, any other questions that you guys may wonder before I just show you quickly what the platform looks like, and then after that, I just put you like a tutorial on how to get kind of started with the new version of TrackMate, and that you can play with some of the data that I've put on the Google Drive.
Okay.
No, so then I'll just give you a quick tour of the Zero Code platform, and then show you what the notebook look like if you've never seen it, and then after that you can play with TrackMate if you want to. So basically, the platform lives on our GitHub page, so that you can find it's hosted by Ricardo's lab. And a lot of the notebooks are accessible via our wiki here. So there's quite a lot of information here on the different notebooks that you can find useful when preparing data, especially. There's some videos from different talks and tutorials that kind of can also help you getting started if you want. But basically here, we just have a very simple table that contain all the different, or link to all the different notebooks that are currently provided. And just here to answer one of the earlier questions, we have a table dedicated to what is called the bioimage.io notebooks. So those are notebooks that if you train a model there, you can export them for DeepImageJ. So if you're especially interested in generating model for DeepImageJ, those are currently the ones that are available. And then a few others that kind of not to train deep learning networks, but kind of provide tools that can be useful. So if you want to just do data augmentation, or if you just want to do quality control, but you don't actually want to do any training, then we have a notebook here for that as well. And then if you want to access the notebook, so it's very simple. You just click on the button you want to use. So here I'm just going to open the Stardist 2D notebooks that I wanted to show you, to just stay in theme with Stardist and TrackMate that I was just showing you. And basically, the notebook is a combination of text and code. So if you scroll down the notebook, you will not actually see any code because the code is hidden by default. But if you want to see it, you can just double click on it and you can access it. Basically, as I was telling you, so Google Colab, if you've never used it, is basically an environment provided by Google to run code and then give you access to a GPU. So I have to say, not always access to a GPU. So because again, that depends on the overall usage of Google Colab. And then with the free version, you may not always have access to a GPU. So now I've just connected to a remote session. and then I will see. So now I have access to a GPU. I've got access to a remote computer with 12 gigabytes of RAM and a bit of disk space. So that kind of gives us space to do a little bit of work there. On the side here of the Google Colab platform, you have access to files that are available to you via the environment. And then here, basically on top of the notebook, you have a lot of explanation of where the StarDist come from. So we are, of course, not the developers of StarDist. So here you can find all the information about the tool, the different papers, and where to find the code for StarDist.
Guillaume, I would have a tiny little request.
For sure.
Could you magnify a bit your web page, because it's quite hard to see from our side. Okay, thank you. Yeah, perfect.
Okay, good.
Thank you.
No, thank you. So here you have access to a small computer where you can have access to RAM and disk space. And here you have your file. So when you click on that little folder here, you have access to the files that you have here. So the good thing with Google Colab is that the environment comes with a lot of libraries pre-installed that are useful for machine learning. So there I'm talking about Torch, but also TensorFlow and CUDA, and you're already directly connected to a graphic card. So a lot of the painful things that you need to do to set up your environment is already done here, and you don't have to worry about it on your own computer. So at the top, there's a lot of text explaining how the data needs to be organized and what is the notebook expecting. So those are really useful information for you to read when you start using those notebooks. But for now, I'm going to slowly scroll down. And then one of the things that also we try to do is that all the notebooks are organized in exactly the same way. So if you learn how to use one notebook, then moving to a different notebook should be relatively straightforward, because all the terminology and all the structure of the notebook is the same. And you always start by installing the things that are missing from Google Colab, which is here installing StarDist in order to be able to do prediction. Of course, that's one of the downside here of using Google Colab is that you need to reinstall the library you need every time you want to use it, because of course it's not kept by default in the Google Notebook, but at the same time it only takes a couple of minutes, so it's not that painful to do. So now it's we are downloading and installing one version of StarDist that works quite nicely, and then we're going to kind of enable all the right dependencies that you need to be able to run StarDist over here. What's going to happen at the end here of the installation is that the runtime is going to restart, because StarDist, even though it's being updated really actually very regularly compared to most of the other deep learning tools. I have to say there the authors are doing an amazing job at keeping StarDist running well. Still, Google Colab is packing a more up-to-date version of TensorFlow that StarDist does not work with. So then we need to reinstall the proper version of TensorFlow and then restart the runtime. That's why you get your session crash here for an unknown reason. So we just restart it in order to enable the new library. So now everything is installed. We just need, as for any Python environment, you just need to load all the dependencies that you need to run your code. And then here we also load some of the functions that we need to run the notebook. So here we're using a fairly old version of TensorFlow. So for some of you that are interested about these things, the main reason here is that the model that you can train in this notebook is compatible with StarDist that run in Fiji, and TensorFlow in Fiji is only the fairly old version of TensorFlow that runs at the moment. So that's why we use here a quite old version of TensorFlow. Okay, so now the environment, everything is set up. So hopefully, as you can see, it's relatively easy. You just have to press here on the arrows to run the code, and then you have some text explaining on how it works. So here you can check what kind of graphic cards Google Colab has allocated to you. So here now we have access to a Tesla K80, which is the worst one that Google Colab provides. But now that's the one that we always get in the free version. So before we used to be able to have access to better graphic cards. But now I think they keep those only for the people that give them money. unfortunately. But it doesn't matter too much. With a test like AAT, we can still do quite a lot. Then after that, you basically can connect to Google Drive to access your data. And then that's also relatively straightforward, where you just click on the code, and then you can just copy the authorization link to be able to access your Google Drive data here. So we're going to publish a guide on how to do that. You can do that with AirSync. It's a little bit less straightforward, but it's also definitely possible. So now follow the instruction, and then now I have my Google Drive here on the file tab on the side. So now we're all set up, ready to go. And then basically what we want to do is to start training a network, right? So that's what we can do now. And the first thing you need to do is basically choose what kind of parameters you want to use to train StarDist, and then basically tell where your data are. And that's what you can do here. So that's what I meant by the very simple graphical interface. It's basically a simple form where you can indicate where your data are and then what kind of parameter you want to use. In the zero-cost deep learning notebook, we called training source and training targets. So training source is basically the data that you start from, and then training target is what you want your deep learning model to achieve. So basically, how do you train? It's always from A to B. And so here I'm going to go and navigate towards the StarDist data set that I have, that I've also put in the Google Drive of the workshop, in case you want to also do it later on. So I've got a training StarDist model here, and then I have training images, and then the mask here. So here you can just right click to copy the path on the side, and then put it here, and then here is a mask, so copy path, and then here. Then you can decide how you want to call your model. So here I can call it test, something like that, whatever name you want to give it, and then where you want to put it. So I will put it in my model folder. And then here you can then decide what kind of setting you want to use for the training. So I unfortunately don't know how much you've heard about these type of things before this particular workshop, but one of the main things that you need to decide is how many epochs you want to use for the training. So it's how many rounds of training you need to train the deep learning network. So typically, if you start the training from scratch, then you probably want to train for hundreds of epochs. Here, we won't have time to do that, so I will just train for 10. And then after that, there's a lot of different other parameters you can, of course, modify as well to change the training. But most of them are kind of more advanced parameters you might not need to play with at the beginning. So we've kind of worked out some, or not just us, but also the StarDist team work out some kind of default parameters that works for a lot of different applications. And then when you've chosen all your parameters, and again, you run the cell. And then here, if all goes well, then you should have an image of what your data should look like. And then here I can see that I've already put the wrong path for my training source. So I've put the mask twice. Okay, so here I don't want to train mask to mask. I want to train images to mask. And then I can rerun the cell here. So hopefully that should work better. Here are some nuclei, and then here are the manually annotated mask that goes with it. So I was telling you, so the code is not visible by default, but if you just double click on the cell, then you can see all the code underneath. So if you are interested to see what's underneath, or if you want to modify it for your own purposes, then you can, of course, do that easily. And then after that, in the kind of traditional deep learning pipelines, then there's kind of things that you can consider. One is whether or not you want to use data augmentation. So data augmentation is a way of increasing artificially the size of your data set by doing manipulation on your images. So it's used a lot, especially for segmentation, because you can multiply your data set by 8 by just flipping and rotating your images. But then you can also further increase the size of your data set by changing the amount of noise, for instance, or the quality of the data. And that can improve how well your data set or how well your model is performing on new data quite a lot. So here we're not going to do that. Another thing that you can, of course, do when you train a deep learning model is to decide whether you want to train a model from scratch. And what does it mean? It means that you start with a blank model where all the weights inside of the model are randomly assigned. Typically, this is maybe what you will do. But if a model already exists that kind of do what you want relatively well, but not perfectly, then what you can do is instead to do some transfer learning or tuning of your model. And then here, for instance, because we want to segment fluorescent nuclei, the versatile fluo nuclei that is provided by the STARDIS team is already doing quite a good job. It's not perfect. We can improve it further by retraining. But if we use that as a starting point, then that can accelerate the training quite a lot instead of starting from a blank model. So here we're going to do that so that the training is faster, then you have time to see it. So here we have access now to this model. And then instead of starting from scratch, we're going to start now from this model. Okay. And then finally, we can start training. So then there, you need to prepare now the data so that it's in a format that can be used for training. And very often that means patching the images, or it also means pre-processing the data in order to start the training. And so this is what this cell does. So you don't really have anything to do here except just wait for all the data to be pre-processed before the actual training starts. So here the pre-processing could be already included directly in the training cell, but we've decided that it's a nice kind of way of also a kind of learning of the different step of the whole deep learning pipeline to kind of realize that there's quite a lot of data manipulation done to your images before you actually start training. So that takes a couple of minutes. And then after that, we can start the actual training. So here, one of the things that you can do in Google Colab is to run the cell one after the other. And then if you just already activate it, then it's going to just wait until the previous cell is finished, and then the other one starts straight away, which can be useful if you want to do something else in between. Any question up to there while we wait for those things to work?
Hello, it's Romain.
Hey, Romain, nice to see you.
Another Romain. I was wondering, you were talking about reusing the STARDIS model when you do a new training.
Yep.
And what about the data? Do you only use your own annotated data or also pull the one from the DSB challenge?
No, so here we just reuse our own annotated data. So then here we basically annotated, so I didn't want to show it to you guys because actually you already have quite a lot of things on annotation. But what we do a lot in my lab is that we use STARDIS to annotate our data and then we correct them. And then we use those annotated images to kind of fine-tune STARDIS so that it works better with what we want to do. So what it does is that it creates models that are really specific to our own little problem, which is of course great for us because it works really well for our own images. But then if we start sharing those, then it might not work so well for other purposes. Okay, so now the data has been pre-processed and now it's starting to train. Any other question while the model is training?
Yeah, I got one.
Go for it.
Hi, Guillaume. Do you manage to get TensorBoard using Google Drive and Google Colab?
Yes, you can. You can have TensorBoard, yeah.
Okay, because that would be interesting to see what's the code and how you manage that, because I think it's quite useful
Yeah, so TensorBoard and Google Colab is actually really easy to load because there's a magic function to make it work. So like one line of code to load it. So it's possible. You can even follow the training in live if you load it before the training.
Okay, cool.
So now it's slowly training. So we don't have so many images in that particular data set. I think it's about 40 annotated images. And then here you can see that the training is divided in different epochs. So the round of training. And then each of those epochs is divided in different steps. And that's basically because all the images do not fit in the GPU for training. So that's a thing. Of course, you will want to look at all the images at once if possible, but here the GPU is not powerful enough to do that. So then you need to divide the training in different steps. So one thing I should say is that, of course, it's not something that everyone agrees on, but typically what we see as an epoch is one round of training. So it's one round where the network see all of your images at least once during training. So that's why here we have that many steps. So that depends on your batch size. So a batch is in one step how many images you see, or the deep learning network see. So whatever fits in your GPU, and then at the end of the 23 steps, then the network has seen every image in the training data set at least once, if that makes sense. So here we're training again for a very short amount of time, so that I just have time to go through the pipeline relatively quickly with you guys. But if I were to train a model properly, especially from scratch, then I will train for maybe 200 epochs for this. And that generally takes about 2 to 3 hours for StarDist 2D. So then of course that doesn't fit in that 20-30 minute demo that we have planned here. Okay, so now training is done. So one of the things that happen in StarDist is that you optimize the network to get the best possible results. So because StarDist has a lot of post-processing steps to do the instance segmentation, so there you're using your validation data to get the best possible post-processing in order to get the best labels being generated by the network on the training data. And then once this is done, basically this is all. So you've trained your StarDist model. So hopefully you can appreciate that it's relatively simple, and then hopefully this is something that everyone can manage. So the hardest part is here now, at least for us, is now to spend the time annotating the data. So now the model is in here. So here it's my test 2. Then in there you have a lot of files that contain your model, and then you also have a model exported in the zip file. So that's the file that you can use, for instance, in the StarDist Fiji plugin in Fiji, if you want to do that. And then we also produce a PDF file that contain a training report that basically kind of write down what you've done here. So here, kind of in a text format. Maybe it's a bit too small. I can zoom a bit. So what kind of setup you've been using, and so on. What parameters have been used, and where are your data stored, and so on. So that can be useful to remember what you've done, but also if you want to kind of generate model for others, then you can send that as a report together with the model. Okay, but and then some things I will talk a little bit more about later, but here I can also highlight it is, well, of course, one thing that's important to do once you've generated a new model is to evaluate it to see how well it works. And that's basically the step 5 now in those zero-cost deep learning for microscopy notebook, is that you can directly do the evaluation. Of course, for that, you need to have specific testing data that you've put on the side. The first thing you can do is to test the loss function over time, so over training time. So here it's not that useful because we've trained for only a very short amount of epochs, so you're not going to see much going on in those curves. But if you now start to train a model from scratch for 200 epochs, then you can start to look at whether or not your models start to overfit or things like that, for instance. And then I think something that's maybe the most important in terms of quality control, and then is to start to use quality metrics to assess on how well is your model working on the data set you want to analyze. And then here there is a cell to do that. And again, so that's something we will talk more about this afternoon. But basically here you can provide to the notebook test data and masks to see how well is your model working. So here is the data that I have here. And then some test masks that goes with them. And then basically what's going on is that you now make prediction using the model you just trained on the test data, and then you compare the prediction to the mask that you provide. And then you can get quite a lot of quantitative metrics checking on how well is your segmentation working. Here, for instance, you get quite a lot of different metrics for those instant segmentations that we will discuss a bit more this afternoon. So false positive, true positive, false negatives, and so on, that you can start properly evaluating how well your model is working. And then finally, most likely, if you train your deep learning model and if you're happy with the quality control, you probably want to use that to analyze data. And so that's what you can do now in the step 6, where you can generate predictions based on your data. And then here again, all you have to do is to put where is the data you want to analyze, what model you want to use. So if you want to use the one that you just trained or another model, what kind of data you want, and then also what kind of data you have. So here so far I've only shown you single images, but here it's also possible, for instance, to analyze stacks. So here I'm talking about 2D stacks, so 2D plus time, for instance, where you will want, for instance, to analyze videos or something like that. Then it's possible to analyze that here directly without going for generating single images, for instance. And then finally, something that may also be useful is that if you want to analyze really large data, so very large images, then it's also possible to do that here. So if you have gigapixel size images, then it's also possible to do it here. And then there under the hood, it works a little bit differently, where we are not loading TIFF images anymore. Then we first save them in a different format using ZAR, and then basically the prediction goes into different patches, and then the way that the image is now reconstructed at the end is done in a much more RAM efficient way than in the previous section. So from here, if you have really, really large images, then it's good to use this section rather than the other one, where you might start to run out of RAM, for instance. And then after that, everything is saved in Google Drive, so you can download them. And then at the end, we have a version log since one of the latest version. So then you can also have a look if what's changed since the latest version. Okay, so that's kind of a very brief overview of what a zero-cost notebook look like with StarDist as an example. But now, if you go to kind of different things like I don't know, let's go for denoise-seg, for instance. Then when you open the notebook, you will see that the structure is exactly the same, and then you will maybe not actually see that many differences. So then everything is going exactly the same thing, exactly the same structures. The parameters are called the same, so hopefully you don't need to kind of start worrying too much about that. There are, of course, network specifics things, because some of the parameters are, of course, different between deep learning networks. Here is another example for CellPose, which is, of course, I think a really, really useful tool where you can do some segmentation using some of their excellent pre-trained model. And there you can also train CellPose, but if you don't want to train CellPose and want to use it to make prediction, then we've also incorporating their pre-trained model here in the prediction, but also in the quality control. So there you can use, for instance, the different where I find it. Yeah, you can use a different model provided by Cellpose or your own if you train it yourself. Okay, so that's kind of what I wanted to show you. So is there any question about some of those notebooks before I let you play a little bit with the new version of TrackMate?
It seems that there are no questions for now.
Okay. Then if there's no question for now, then I put like a small exercise in the, I don't know if you've seen that already, but in the Google Drive, so I can open it here again, of your workshop. Where is it? Google Drive. Yeah. There's a folder called Jeudi in datasets, zero cost deep learning for microscopy here. I've made a PDF here that contain basically a lot of the things that I've shown you, and as well as a small exercise if you want to play with a new version of TrackMate. And the data are here as well. So there here I've just trained StarList using the data that are in this folder. So in case you want to also do it, then you can do that. And then some of the data we're going to use this afternoon are also in those folders. So I don't know if you've already downloaded those data. If you have them on your computer, then if not, then you could look at them. And then in the PDF file here, basically there is instruction on how to get started with StarList in TrackMate with the data that I have here. So if you want to start playing with that, then I think here I'm happy to kind of discuss that more. And then I think it may be the easiest is that I can also slowly do it on my screen while I share the screen, and then we can maybe go forward like that. Donc, vous pouvez commencer à suivre les instructions. Et puis moi, je vais le faire tout doucement de mon côté, en partageant l'écran. Et si jamais il y a un problème quelque part, n'hésitez pas à hurler ou faites ce que vous voulez que je puisse vous voir, et on essaie de régler ça. Donc, si vous avez réussi à récupérer l'image, c'est à ça que ça ressemble. Il y a des cellules cancéreuses avec les noyaux qui sont ici labeled. Et donc, bon, StarList, c'est bien sûr très bien pour détecter ce genre de choses. Et donc, si vous voulez commencer à faire du tracking avec TrackMate et StarList, vous pouvez ouvrir TrackMate. Donc, ça se trouve dans Tracking et TrackMate. Au début, vous allez voir si les infos sur l'image sont bonnes, et puis vous appuyez juste sur Next. Et après, au niveau TrackMate, vous pouvez juste choisir quel type de détecteur vous voulez utiliser pour faire la segmentation. Et donc, vous pouvez choisir le détecteur que vous voulez utiliser pour faire la segmentation. Donc, TrackMate, comme beaucoup d'autres tracking algorithmes, vous devez d'abord segmenter les objets que vous voulez traquer, suivre, et ensuite les suivre. Et donc là, on va utiliser StarList. Donc, tout dépend de comment est-ce que vous avez installé TrackMate et quel update site in Fiji vous avez utilisé. Mais si vous les avez tous installés, vous avez accès à Veka, Morpholib, Elastic et plein d'autres détecteurs. Et là, on va utiliser le StarList détecteur. Si vous générez vos propres modèles StarList en utilisant par exemple Zero Cost ou le StarList in Python, vous pouvez aussi utiliser vos propres modèles StarList ici directement. Donc, on choisit le détecteur StarList. Et ça, en fait, ça utilise le StarList Versatile Fluo Model qui est installé par défaut dans StarList. Et donc, quand vous appuyez sur Suivant, il y a un petit peu d'explication d'où est-ce que ça vient. Et vous pouvez appuyer sur Preview ici pour voir à quoi ressemble la segmentation de StarList ici, pour voir si c'est bon ou pas. Et donc là, vous voyez déjà que Stardist, il fait du très bon boulot pour détecter les noyaux. Mais un problème qu'on a ici, c'est que comme l'image ici, elle a beaucoup de noise, mais aussi des imperfections qui viennent de la façon de l'échantillon, en fait. Stardist aussi croit qu'il y a des noyaux dans ces endroits-là. Donc là, c'est un des exemples, par exemple, si vous voulez améliorer ce genre de segmentation par Stardist, ça vaut le coup d'entraîner un modèle directement vous-même pour retirer ces choses-là. Mais ici, dans TrackMate, on peut les filtrer après, donc on peut aussi s'en passer. Donc, si vous êtes content avec le preview, vous pouvez appuyer sur suivant. Et puis, en fait, ce qui va se passer, c'est que maintenant, TrackMate va utiliser Stardist derrière pour faire la détection. Et donc là, il y a pas mal d'images, donc ça prend quelques minutes pour faire ça. Et ça dépend aussi, bien sûr, de votre laptop aussi. Donc, si vous avez une graphic card, si vous avez un processeur plus puissant que moi, ça sera beaucoup plus rapide.
Ça marche? Je ne demande pas.
Est-ce que tout le monde a réussi à aller jusque-là pour le moment?
Je crois que c'est bon là, Guillaume. Donc, toutes les détections et ils piaffent tous d'impatience.
Ouais, là, ça va.
C'est bon tout le monde? C'est bon?
Super. Donc, au niveau, dans le même dossier sur le Google Drive, je vous ai aussi mis un de nos modèles Stardist qu'on a réentraîné avec Zero Cost, qui performe mieux en fait que le Versatile Fluo. Donc, vous pouvez aussi avoir accès à ça ici. Donc, si vous voulez ensuite utiliser ça pour voir quelles sont les différences, c'est ici dans le Custom Stardist Model. And then ici, il y a un modèle.zip. Donc ça peut être utilisé directement soit dans le Stardist Fiji plugin ou soit dans TrackMate pour faire les détections. Et ici, ça a les informations à propos de comment est-ce que le modèle a été entraîné et le QC report pour le quality control.
Guillaume,
oui?
J'ai une question, c'est comment parce que là, on a vu la liste déroulante des différentes modalités de détection pour TrackMate, mais comment tu mets ton propre modèle dans TrackMate, justement? Ça, j'ai pas...
Pour utiliser Stardist dans TrackMate avec ton propre modèle?
Ouais.
Ok, il y a un des détecteurs. Je vous le remontrerai après. C'est un des détecteurs. Il y a un détecteur Stardist et il y a un détecteur Custom Model pour Stardist.
Ah, Custom Model. Et donc là, il te demande sûrement un lien vers le zip.
Voilà. Quand tu choisis ça, il te demande en fait de choisir un fichier à utiliser pour faire la détection.
Et si jamais, Guillaume, tu peux aussi utiliser des labels. Si tu as déjà, par exemple, Cellpose qui n'est pas encore en TrackMate ou un autre truc pour générer des labels, tu peux aussi partir de ça, c'est juste.
Tout à fait. Si tu as déjà des labels, tu peux les utiliser en fait. Et il y a un détecteur pour label image et en fait, tu peux déjà faire directement le tracking avec ça. Donc là le seul avantage, en fait, si tu veux, tu peux utiliser Stardist pour instance dans le notebook Zero Cost et exporter les labels et ensuite faire le tracking avec les labels. Donc ça peut avoir un intérêt, par exemple, si les ordinateurs auxquels vous avez accès sont vraiment pas bons, parce que du coup, il n'y a pas besoin c'est beaucoup plus rapide, en fait, de le faire comme ça.
Et une dernière question.
Pour recréer ton modèle que tu as mis en ligne, tu es parti du coup du modèle pré-entraîné versatile Fluo ou tu l'as
en fait, on a refait exactement comme je vous ai montré. Parce que là, le Versatile Fluo, il marche pas mal, mais il y a des erreurs. Alors du coup, on a fait du transfer learning dessus pour corriger les erreurs. En fait.
Merci.
C'est bon?
Et donc, dans mon labo, on fait beaucoup du high throughput. On a beaucoup de vidéos à analyser. Et donc, du coup, on fait parce que ça prend 5 minutes par vidéo sur mon laptop. Du coup, la détection, on le fait aussi souvent sur Google Colab, en fait, parce que c'est beaucoup plus rapide. OK, donc maintenant, une fois que ça, c'est fait, on peut, ça c'est le gros avantage de TrackMate, en fait, c'est qu'avec le graphical interface, il y a beaucoup de possibilités. Une des choses, c'est que tu peux faire du filtering et du thresholding. Le premier ici, c'est pour la qualité des détections. Ici, on peut l'ignorer pour cet exercice. Mais bon, après, ce qui se passe, c'est que TrackMate, maintenant, va analyser tous les objets qui ont été détectés et calculer leurs features. Donc, le size, the shape, parameters, etc. Et donc, après, c'est possible, en fait, d'exclure les choses en fonction de leurs paramètres. Donc, par exemple, ici, si je choisis, j'avais mis dans l'exercice en fonction du périmètre, si jamais je veux en fait retirer les choses qui sont trop petites, comme il y a beaucoup d'ici d'erreurs qui sont toutes petites, en fait, c'est assez facile de les retirer comme ça, en les retirant. Et il y a des choses qui sont bien trop grandes, qui ne sont bien sûr ici pas des noyaux, donc c'est aussi possible de le refaire avec des périmètres, si je le retrouve. Et maintenant, je peux choisir tout ce qui est trop grand, en fait, j'en veux pas. Donc, comme ça permet déjà de retirer pas mal de false detection, juste en filtrant, en fait, les objets. Tu peux aussi faire de la filtration en fonction de l'intensité, etc. Ou s'il y a une autre channel, s'il y a d'autres couleurs pour ces vidéos-là, c'est possible aussi de faire ça sur d'autres channels. Après, bien sûr, pour le tracking, ce qu'il faut faire, c'est connecter les différents objets entre les images. Et donc là, il y a pas mal d'options pour faire ça aussi dans TrackMate. Ici, on va utiliser le Lab Tracker qui permet en fait qui autorise les cellules à se diviser en fait. Parce que là, il y a quelques divisions cellulaires dans cette vidéo-là. Et donc après, c'est une question en fait de choisir les bons paramètres en fait pour faire le tracking. Donc là, je vais aller un peu plus vite parce que c'est pas le but ici, mais bon, il y a des cellules qui se divisent, donc on les autorise à se diviser. Et donc là, les cellules ne peuvent pas you can't merge the track, les cellules ne se mergent pas. Et donc 15 micromètres ici, ça marche plutôt pas mal. Et puis on peut appuyer sur Next. Et après, très rapidement, en fait, TrackMate va connecter les détections d'images en images. Et donc maintenant, on a déjà les tracks ici. L'autre chose qui est aussi très très bien avec TrackMate, c'est que on peut aussi filtrer les tracks en fonction de leurs paramètres. Et donc, vous voyez ici la plupart des détections qui sont mauvaises ici. En fait, les tracks, elles n'ont pas bougé parce que ces objets-là, ils ne bougent pas. Donc, c'est possible de retirer en fait les tracks qui n'ont pas beaucoup qui ne bougent pas en fait. Donc là, c'est la distance de displacement, et donc ça exclut pas mal de ces tracks ici pour garder seulement les cellules. Après, l'avantage de TrackMate, c'est qu'il y a pas mal d'options de visualisation. Donc, par exemple, tu peux choisir de voir les tracks entières ou de voir seulement les tracks in local time. Donc, ça peut être choisi ici. Tu peux choisir combien il y a de tracks, de time points. Et puis, il y a pas mal de settings ici pour décider de qu'est-ce qui est displayed. J'oublie mes mots français. Et aussi la line thickness, qui est très utile ici si on veut faire des vidéos un peu plus jolies. Donc, si on veut exporter maintenant les données, on peut appuyer ici, par exemple, sur Tracks. Et donc là, il y a maintenant un tableau avec toutes les spots, les tracks et leurs properties, donc speed, etc., qui sont maintenant disponibles. Le grand avantage de la nouvelle version de TrackMate, c'est que maintenant, comme il y a des outils de segmentation qui marchent très bien, c'est que le shape des objets est maintenant available. Donc, par exemple, si tu vas si vous allez sur l'option Spots, il y a des possibilités d'avoir pas mal d'informations sur les changements de shape over time. Yeah. Et puis, à la fin, c'est possible de faire des vidéos, par exemple. Donc, si maintenant, j'exporte ça, je vais pouvoir créer une vidéo des cell tracks, comme somme des vidéos que je vous ai montrées dans ma présentation au début. Donc, c'est juste pour vous montrer un petit peu comment ça peut. Maintenant, on peut utiliser, par exemple, Stardist avec TrackMate dans cet exemple. Maintenant, si je retourne tout au début pour la question que j'avais eue avant, mauvais dossier, avant de vous laisser prendre une pause. Non, ça, c'est mauvais fichier. Maintenant, si je vais dans Tracking, TrackMate, c'est possible de choisir un modèle Stardist que vous avez entraîné vous-même. Donc, il y a un détecteur spécial pour ça. Et donc là, vous indiquez juste l'endroit où est ce modèle. Donc, moi, je l'avais mis ici sur le... Et je peux le choisir. Et du coup, maintenant, avec mon modèle qui est un peu plus adapté à ces données, je n'ai plus toutes les identifications qui ne marchaient pas ici sont retirées et j'ai des meilleures better segmentation of the nuclei. Donc ça, c'est l'avantage principal de réentraîner vos modèles pour avoir les meilleurs résultats possibles sur vos images.